Hello friends, let us start our study on laws of motion. To begin with, let's see what forces are. A push or a pull, in very simple words, which is applied on a body to change its state of motion or its orientation, is called a force. As you see in the picture, a person is trying to push or pull a body in order to change its shape or trying to stop it from motion. Forces can be of two types: contact forces and non-contact forces. Contact forces are those which require a physical contact or a touch for their application. Most common of these forces being normal force and tension force. In going in detail about normal force, whenever a body touches another body, there is a mutual force between both of them, which is called normal. It is always a pushing force and it always acts perpendicular to the common contact surface. Next, let's talk about tension. Tension. The first thing that will come to your minds would be a thread or a string that pulls you. Yes, force applied by threads, chains, rods, etc. are called tension forces. Tension is always a pulling force. A string, as you see here in these pictures, can apply a force, can apply tension only if it is taut and never when it's slack. Non-contact forces or field forces. Some forces can be applied without a physical contact. Very basic, the gravitational force that keeps all our planets orbiting around the sun. Yeah, that's like the simplest example for a non-contact force. There is no actual contact between the planets and the sun, but still they keep orbiting around it. Then we have the electromagnetic forces, nuclear forces, and the weak forces. As you see, the magnet attracting the nails, the CD which is rubbed, that is charged, attracting the small pieces of paper which brought near them. A few examples. Now let's move on to Newton's laws of motion. Newton formulated three laws. The first one being the law of inertia. It states, if a body is at rest or already in uniform motion and you try to change that state, the body will resist the change. This property by which the resistance is offered to any change in state is called inertia. Based on situation, inertia is of three types: inertia of rest, inertia of linear motion, and inertia of direction. For example, a very common thing we experience in daily life is while driving, when you suddenly apply brakes, your body jerks forward. That is because your body does not want to stop its motion. That is, it still wants to keep moving forward, and so it resists the stopping by actually moving forward. The picture that was there on the first slide, the glass with the coin. Yeah, it's a simple experiment that shows inertia of rest. A glass with a cardboard kept above it and a coin is placed on the cardboard. Now, when the cardboard is pulled out, the coin, which is heavy and has inertia, does not want to move along with the cardboard and stays at rest, falling into the glass. This sudden motion of the cardboard shows how the inertia of rest of the coin is displayed. And when you dust your carpet, as you see in this image, when you give it sudden jerks, the dust particles do not leave and try to stay in their rest position, which in turn leads to the dust going out of the carpet. In mathematical or quantified form, inertia is mass. That is, as you see in this last picture, it's easy to move this bucket without the sand, but tougher to move this one. That is because This has lesser mass and so lesser resistance to change in state of motion. Now let's move on to Newton's second law. It states that to change the momentum of a body, a force is required. This is the simplest way of stating the Newton's second law. Mathematically, to prove this, we say momentum, which is mass into velocity. The rate of change of this momentum is proportional to the force applied on the body. Here, proportionality constant is 1, so we get dp by dt is equal to F vector, that is the force vector. Substituting P is equal to mv, we get F is equal to m dv by dt plus v dm by dt. In general ideal cases, we take mass being a constant and doesn't change with time, so dm by dt is equal to 0, and thus force vector is equal to m into change in the velocity vector over time, which gives us F is equal to ma, where F is a net external force on the object, m is the mass of the object, and a is its acceleration. Newton's third law. This is what we have all heard everywhere, that for every action there is an equal and opposite reaction. But there is something important to it that you must remember, that an action and reaction always act on two different bodies. In the coming slides, I'll explain how this is true. But if body 1 applies a force on body 2, then body 2 will apply the same amount of force on body 1 in the opposite direction. That is, the action and reaction are happening on two different bodies. This is the mathematical form of the same law. Next, an important part of Newton's laws, the free body diagrams. These are very important to solve any kind of questions that you get in this chapter. Now, what is free body diagram? It is representing a body isolated from its surroundings, showing all the forces acting on it. As you see in this example given, the cart is being pulled by two kids, but to analyze the forces on it, you take it separately away from its surroundings and write all the forces acting on it, thus finding equations and solving the net force on it. A very important note that we must remember is that normal and mg being the gravitational force or your weight which is applied on any object, are not part of an action-reaction pair. That is, reaction of normal on the block is the same normal in the opposite direction on the table. But this being the free body diagram of the block, we will not show the other normal being acted on the table. Secondly, the reaction of weight, which is the gravitational force, is always applied at the center of the earth in the radially outward direction towards the block. Free body diagram for spherical bodies. For spherical bodies, as we see here, any force that is applied, this being a wall, will provide another normal. But all normal reactions are considered to pass through the center of the sphere because it is perpendicular to the tangent at that point. We know that normal forces always act perpendicular to the contact surfaces. So if a normal has to act perpendicular to the wall and the sphere, it will obviously pass through the center of the sphere. Similarly, when there are more than one spheres kept on each other, we can still find out the normal forces by analyzing each one of them separately and writing equations. Now, a very easy problem. Find the acceleration of each block and the normal force between each of the pairs. Now we can see how to analyze each block separately these being the masses 2m, 3m and 4m, and we are applying two forces, 3F from one side on 2m and F from the other side on 4m. We separate the blocks and analyze them as single systems, which gives us few equations. As the first one, 3F minus N1 is 2ma, which is the net force equal to mass into acceleration, as we saw already in the Newton's laws, and similarly for all the other bodies. And we write them down and we figure out that the acceleration of each body must be the same and equal to 2F by 9m in this case. Similarly, the normal between the blocks can also be found out by solving these equations. In general, we can formulate an easy way to find out these normal forces, which is given by F12 is equal to m2 by m1 plus m2 into F. Here, this is the force applied on m2. In a similar way, if there are more than two blocks, you can still find out the force applied by one block on the other using a similar formula. Let's go in detail about tension force. As I already said, these are applied by strings, which can be of two types, ideal strings and non-ideal strings. In our case study, we will almost all the time consider ideal strings, which are massless, inextensible, frictionless, and tension at all the points on such strings will be the same. Now, what are non-ideal strings? They have mass, like in a rope, may or may not have elasticity and friction, and the tension at different points on the string will be different. For an ideal string to be taut, the acceleration of its endpoints, that is, in this case let it be A1 and A2, should always be same. That is, if A1 is greater than A2, then the string will become slack and that condition won't work. If A2 is greater than A1, the string has to extend, and for an ideal string which is inextensible, it's not possible. So for A1 equal to A2, it remains taut and moves. As a note, we must remember that for an inextensible string, the component of velocity of both of its ends along the string must be the same. As you see in this example, this body has an upward velocity of v and this one has a sideward velocity of v0. Now, we are supposed to find out what is this v in terms of v0. We are supposed to split this v0 into its components, that is v0 sine theta and v0 cos theta, where this is an already given angle theta, and we get v, that is this velocity, should be equal to v0 cos theta. That is because both ends of an ideal string should have the same velocity along the string. So along the string, the velocity of this point is v, and along the string, the velocity of this point is v0 cos theta. So these must be same. Next, let's learn about pulleys. A pulley is a simple machine that is used for easy transportation of objects. In our case, we study about ideal pulleys, which are massless and there is no friction on these grooves. So the thread or the rope which moves on it can easily, smoothly move without rotating this pulley. Now, we must remember that if a pulley moves by a distance x, then both sides of the pulley are moving and the string length will change by 2x. That is, when this pulley moves down by a distance x, a thread which is wrapped around it will release 2x of its length. This will be let you analyze questions more easily in future. This is a very simple question which might look complicated because of the number of pulleys, but is easy if you analyze each of them separately using free body diagrams. Now for A, considering this tension to be T, this mass is given as 10 kg. We know that if on both the sides the tension applied is T by the thread, this being an ideal thread will have the same tension across all its points. So this being T and this being T, the net upward force will be 2T in order to balance them. For the mass, if we draw the free body diagram, this tension, if it has to balance this weight, will be equal to its mg, that is 10 kg into the gravitational pull. Next for B, in a similar way, if you draw the free body diagram, you can say that this is 2T and again this is 2T and this. So we are supposed to find the mass of this body, which using this free body diagram we can say that 2T and 2T will add up to 4T here, and that 4T should equalize the weight of this body, which gives us the weight of this body will be equal to 40 kg. Next, we're going to learn about a constraint relationship, that is the T dot V method to solve such relations. Now, since the string that we use is ideal, it cannot do any total work on the system of masses connected to it. Hence, if we take this to be our string in a random position and this is taut with a tension T, any small motion of point 1 and point 2 will create the net work done, which is 0. So dW1 plus dW2 is equal to 0, which gives T, which is the force, dot dx1 by dt plus dx2 by dt is equal to 0. That is force into the small change in distance. Now dW is this T dot dx, and we are dividing it by dt to get the velocity term, since the RHS is 0, and we end up with an equation T dot v1 plus T dot v2 is equal to 0. So for n number of objects attached to the same thread, you can write sigma I equal to 1 to n, T dot vi is equal to 0. This is applicable only for ideal strings. Some points to be kept in mind are, as I already said, that this is applicable only to ideal strings, that is massless inextensible ones, and the displacement of all the masses must be written with respect to the ground frame or any stationary frame, that is the place we look from should be stationary. A few examples that you can look on to. Here we analyze this system as a single one using the T dot V analysis. Here we know V1, we know V2, and we are supposed to find a relation between both of them by writing T dot V1 cos 0 degree, because V and T are in the same direction. Any dot product will be equal to mod T mod V into cos of angle between them, that is what is written here, plus 2T on this block into V2 into cos 180 degree, because tension and velocity are in the opposite directions, should be equal to 0. Now we get V1 is equal to 2V2. In a similar way, if a lot of pulleys are connected with a lot of masses, we can still find out by considering each and every mass. For this mass, T dot V1 cos 180 degree plus here T gives 2T, T gives 2T. So the net force on this block will be 4T. 4T into V2 into cos 0 degree is equal to 0, which gives 4V2 minus V1 is equal to 0, and V1 is equal to 4V2. The next we move on to rigid body constraints. The similar way of finding out velocities and accelerations by using few other formulae and simple analysis of forces using its components. Now when two rigid bodies are in contact with each other, the components of velocities of each along the common normal direction must be the same. This can be a very important tip for you to solve a lot of questions. So along this common normal direction, the velocities of the rigid bodies in contact should be the same. So if a rod is falling onto a wedge with a V1 velocity and the wedge moves away from it with V2 velocity, then V1 cos theta, where theta is the angle of the wedge, should be equal to V2 cos of 90 minus theta, which is V2 sin theta. Now we get V1 is equal to V2 tan theta. Now what is pseudo force? Pseudo, as we know, means false, something which is not the actual reality. Newton's laws are only valid from inertial frames or non-accelerated frames of reference. To justify equations of Newton's law from accelerated or non-inertial frame, we apply something called a pseudo force, which is a fictitious term only that occurs only in equations. FPS vector, which is the pseudo force vector, is equal to mass of object into the acceleration of the frame of reference in the opposite direction, which is given by the negative sign here. To understand the pseudo force concept, let's solve a small sum. A car accelerates forward at a constant acceleration A. Find the angle made by the string with the vertical direction at equilibrium position of the mass with respect to the car. Now, when will this pendulum be at equilibrium with respect to the car? For that, we need to sit inside the car and look at the pendulum. When the car starts accelerating, the pendulum will slowly move back, and after some time, a person sitting inside the car will not see it move further. It will stay there for some time until the car is accelerated down again. So, to analyze this condition based on the car's motion, we apply a pseudo force in the opposite direction of the actual acceleration on the frame. The acceleration of the frame of reference, which is the car, is A in the rightward direction, and we apply m into A in the leftward direction on the object that is to be studied. Now analyzing this object with the same other forces from the ground frame, we get tan theta, which is the angle made with the vertical, is equal to A by G. So theta is tan inverse of A by G, where A is the acceleration of the car and G is the gravitational acceleration. This is a simple way of understanding how pseudo forces work. Next, we move on to the last part of the topic, which is friction. Consider a sliding motion between the surfaces of two bodies in contact. Then a tangential force is developed at the contact surface to oppose their relative motion. That force is friction. Whenever two objects try to move relative to each other, a friction comes in the middle near their contact surface because of the few small microscopic irregularities of its surfaces. This force, which opposes the relative sliding motion between the two surfaces, in contact is called frictional force. It is a non-conservative force, that is, over a path, it will depend on the amount of path you have travelled, plus it will have a total work done even in closed paths. Friction is independent of the relative velocity and the area of contact surface. It only depends on the nature of the contact surfaces. Let's move on to types of friction. First, static friction. This is the frictional force acting on a body when it is at rest. This is a self-adjusting force with an upper limit. Now, what is self-adjusting force? As you see, a block is kept over a wedge in this example, and the F is the frictional force on it, and mg sine theta is the component of its weight along the wedge. If I increase the mass of the wedge, mass of the block, mg sine theta keeps increasing and F along with it will keep increasing. That is called self-adjusting force. F will increase until it reaches an upper limit, which is called the limiting friction. If I increase the mass such that mg sine theta increases that limiting friction, then the block starts moving downwards and the equilibrium is lost. Static friction is equal to the applied force. Limiting friction. It is the maximum value of static friction, as I already said. If an applied force above the limiting friction is acting, then the body will move, and the normal reaction from the body, which is N, can help us find the limiting friction, which is equal to mu s into N. Now, mu s is called the coefficient of static friction, and as I already said, it depends only on the nature of the surfaces in contact. Next, kinetic friction or dynamic friction. This is the frictional force acting on a body when it is in motion. Fk is given by mu k, which is the coefficient of kinetic friction, into the normal of the body. Now, mu static is greater than mu kinetic. This is because until the limiting friction is reached, friction keeps increasing, and when the body starts moving, there's a sudden small drop in the friction, which gives you the kinetic friction. So, mu kinetic is less than mu static. And the last part is rolling friction. It is a frictional force existing when a body rolls over another. Now, this is a sphere which is rotating on a surface which has friction. Now, this is a push that you're applying on the wheel, and the wheel rolls forward, and what helps this rolling is this friction. It helps rolling but resists any kind of sliding between the sphere and the surface. A very common kind of problem that comes under friction is the block on block problem, which reads generally to find the acceleration of the blocks when some force is applied on one of them. Now, this is a common example. The various static friction coefficients, generally we consider static friction coefficient to be equal to kinetic friction coefficient because there is a very negligible difference between them. And so the three different static frictions are given between the different contact surfaces, and is supposed to find out the acceleration of the three blocks when 10 Newton force is applied on the middle block. To find these, you are supposed to draw the free body diagrams of each of the blocks separately and analyze where F1 is the friction between 2 kg and 3 kg. On 2 kg it acts in the forward direction, which is an assumption. If it comes out to be negative, we take it in the other. You need not spend time thinking about the direction of friction on each block. You can just assume it, and then a minus sign in your answer would show you that you're wrong, or a plus sign would say you are right. But the friction on the other block should always be in the opposite direction of your assumed direction. In the same way, for all the blocks, write equations and get your solution. Thank you. Just a reminder, Newton's laws of motion. Remember, every object persists in a state of rest or uniform motion in a straight line unless it's compelled to change that state by forces impressed on it. Second, force is equal to the change in momentum per change in time. For a constant mass, force equals mass times acceleration. For every action, there is an equal and opposite reaction, and the action-reaction pair act on two different bodies. We end our discussion about laws of motion here.